So now we will start to consider functions from the complex plane to itself, like this, or perhaps from some subset of the complex plane to itself. And of course, every such function can be written in this form. You have a real part, which we call u, and an imaginary part, which we call v. Remember that if we write z as x plus iy, so we can split the number z also into a real part and imaginary part. And then, of course, these two functions can also be considered to be functions of x and y instead of just z, like this. So the purpose of this lecture is to deduce some differential equations for these two functions, u and y, u and v, which we'll call the Cauchy-Riemann equations, which are central in the theory of complex functions. And the interesting thing is that there are several independent ways of arriving at these equations. So let me start by considering the approach from vector analysis. So in previous courses we have considered curve integrals of this form over some curve gamma. So gamma typically is given by something like this. Where t runs over some interval like this. So gamma is actually an oriented curve, and then you can compute this kind of curve or line integral. One of the interesting things about these integrals is that under certain conditions on u and v, they will turn out to be path independent. That is, they don't really depend on this curve. Well, they will always depend on the starting point and the end point of this curve. But if you have this as a starting point and this is the end, then it may be no difference in the value of the integral if you integrate along this curve or if you integrate along another curve like this. It turns out, as you hopefully know, that the condition for this curve integral to be path independent in this sense, or at least locally path independent, is that the derivative of this function with respect to x should be equal to the derivative of this function with respect to y. Because then you can really apply the Green's formula to this region here now, and from that you can conclude that this integral must be plus this integral must be equal to 0, which then says that this integral is equal to this integral then. So what we'll do now is to generalize this to complex curve integrals, or what we usually call contour integrals in the following. So we consider an expression like this, integral of fz dz over some curve gamma here now, and gamma can then be expressed as well, you can consider gamma to be given by an expression like this, or of course in terms of the real and imaginary part like this, where t, say, runs from A to B. So what should we mean by a complex integral like this? Well, of course, since we know that z is equal to x plus iy, then of course it's very natural to put dz equal to dx plus I dy. And if we now just insert this expression for f and this expression for dz into here, we'll see exactly what we should mean by a complex curve integral. You see it will become then u plus iv times dx plus I dy. And if we now just compute this to see what it becomes, you see that if we collect the real terms here now, then we first have u dx, and then we'll get iv times I dy, which then will become minus v dy. But then we also have the imaginary part, I times, and then we'll get two terms here, which I write as a new integral, and this will be v dx plus u dy. So the question is now, under what circumstances is this integral path independent in the same sense as before? Well, of course, the answer is that it will be path independent if both the real part and the imaginary part will be path independent then. And so remember, the condition for path independence was then that the x derivative of what stands here should be equal to the y derivative of what stands here. So we'll get the equation that the x derivative of minus v should be equal to the y derivative of u. And so this guarantees that this part is path independent then. And then we have the imaginary part, and the same reasoning here now says that this will be path independent of the x if the x derivative of u is equal to the y derivative of v. So what I've arrived at here is now exactly the Cauchy-Riemann equations. So let me write them down in a little bit more standard form now. So this is the Cauchy-Riemann equations. So del y del x is equal to del v del u del x is equal to del v del y, and del u del y is equal to minus del v del x. Okay, so in this context we have assumed say that the functions u and v, they should be, say, class C1 or something. But clearly these equations are interesting for the same reason that the corresponding condition in vector analysis is interesting. But these can be said to be even more interesting because I'll now show you another way of arriving at these equations, which apparently it looks very, very different, but it will turn out to be another aspect of the same phenomena then. So the next thing is that we just consider the following definition here now. We say that the function f of z is complex differentiable if the following limit exists. So we consider complex differentiable at the point C naught then, if the following limit here if this limit exists. So, of course, this looks very, very much like the definition of a ordinary derivative in the real value theory then. So the name here, complex differentiable, is quite a natural one. But one should observe that this is really a much stronger condition actually on the function, because what we have here is really a two-dimensional limit. So this increment in Z could turn to 0 along all possible directions in the complex plane, not just in directions. They will not just be this will not just be a real number, but it will be a complex number. So we can go to 0 in very many more ways. So let's investigate what the conditions on F should be for this limit to exist. So let's start by considering the case when delta Z is real. So then I just write delta Z is equal to dx then. And remember also that F can be written as u plus ev, and these functions u and v, they can be considered to be functions of x and y then. So then we get the limit here now. The limit when delta x tends to 0, when the real variable delta x tends to 0, of f at the point x naught. Well, I use the obvious notation that z naught is equal to x naught plus I y naught plus delta x then, and then y naught minus x of f of x naught y naught, and then divided by delta x. And if we write this in terms of the real and imaginary part here, then we see that this can be written as y of x naught plus delta x, u of x naught plus delta x, y naught, plus I times v of x naught plus delta x, y naught, and then minus u of x naught y naught plus I times v of x naught y naught, like this. And if we now just split this up into two parts here now, we see that this term minus this term and divided by delta x, it will obviously converge to the partial derivative of u at the point x naught y naught. And this minus this divided by delta x will obviously converge to the to I times the partial derivative of v with respect to x at the same point. Oh, so this is what happens if we let delta z be real. But now we can also let delta z be equal to an imaginary increment, which I then write in this way as I times delta y. And then we instead get the limit now when delta y tends to 0 of, if I write it now like u of x naught y naught plus plus delta y plus I times v of x naught y naught plus delta y, and then minus u of x naught y naught plus I times v of x naught y naught. And then we have to divide by delta z, which is now equal to I times delta y. So what will this expression then converge to? Well, if I write it down here now, you see this term minus this term will obviously converge to, when you divide by this, to 1 over I. You have an I down here, times the partial derivative of u with respect to y. And this term minus this term. Now here you see that all the i's here cancel out. So this will just converge to the usual partial derivative of v. Well, I should write the point x naught y naught here. And then you get the term del v del y x naught y naught. So we note that both this computation here now and this computation we have down here, they are both special cases of what we need to compute in order to establish this limit. We have just taken this limit along the real axis and along the imaginary axis. So if this limit exists, it means that both these two expressions here now, this expression and this expression, they must be equal, because they must both be equal to this, what stands here. And if you now compare just the real and imaginary part, you see that the real part here, del u del x, must be equal to the real part here, which is del v del y, which is the first Cauchy-Riemann equation. And the imaginary part here, which is del v del x, must be equal to the imaginary part here. And if you see, if you multiply here now both numerator and denominator by I, you get minus sign here, minus I here now. So you get that del v del x must be equal to minus del u del y, which is the other equation here now. So summing up, what we see here now is that if we demand this function f to be complex differentiable in this very natural sense, then necessarily the function f, or the real and the imaginary part of f, must satisfy the Cauchy-Riemann equations. So in this way we arrive at exactly the same condition for complex contour integrals to be path independent as for the corresponding function f here to be differentiable in this complex sense.